Great. Thank you for the introduction, John, and thank you to the organizers in general for letting me have the chance to speak here. Yeah, so I've been a big fan of this seminar for a few years now, so it's a great pleasure to finally get to actually talk. So before I jump into the math, I want to make a very quick pitch that I am a fifth-year PhD student at IU working with Chris Judge. And so I'm on the job market this fall, looking for jobs next fall. So if anybody wants to hire me or, take a look at my postdoc application, that would be greatly appreciated. So, right, so let's get to the math. So like the title indicates, I'm going to be comparing Dirichlet and Neumann spectra for the Laplace operator, mostly in Euclidean space, but at the end, we'll talk a bit about manifolds. So let me just get to this setup. Right, so I'm mostly going to be working on bounded Lipschitz domains, so just open connected sets in Rn. And I'm going to be looking at two different spectra for the Laplace operator. So the first is the Dirichlet spectrum, which everybody probably knows about quite well. So these are just eigenfunctions and eigenvalues with zero boundary conditions. And then I'm going to also look at the Neumann spectrum for the Laplacian. So this is where the outward normal derivative is identically equal to zero. And it's well known in spectral theory that since we're working on nice domains with sufficiently nice boundary, that both of these problems have a discrete spectrum that accumulate only at infinity and they consist only of eigenvalues. And so notationally, I want everybody to make note that I'm going to be using lambdas for the Dirichlet eigenvalues and mu's for the Neumann eigenvalues. So that's how they're going to be throughout the talk. And the general question I'm going to ask is, what is the relationship between the mu's and lambdas? And moreover, how does the geometry of the underlying domain affect this relationship? So let's build some intuition for this question. So I've just copied the question here, but basically I'm no physicist, but I want to give kind of a physical intuition coming from music. The Dirichlet eigenvalues generally correspond to the frequencies of a clamped drum head. So when it's clamped on the boundary is not vibrating really. And so that corresponds to the Dirichlet boundary conditions. And so all the frequencies of this drum head correspond to the Dirichlet eigenvalues. And if you imagine unclamping a small piece of the boundary, what you might expect to happen, if you've ever played music, is that the pitch of the drum will lower, right? And roughly speaking, what this unclamping does is it creates a kind of Neumann component of the boundary. And so if you imagine unclamping the entire boundary, theoretically, what you get is the Neumann eigenvalues, or the frequencies correspond to Neumann eigenvalues. And so what you expect from the physics here is that the Neumann eigenvalues in general are less than the Dirichlet eigenvalues. And it turns out this isn't very hard to prove at all. If you know the min-max theorem, you can prove this in a line. So that's a true fact. So what we have is that mu j in general is less than lambda j. And so the new question is, can this be strengthened somehow? And how do I want to talk about strengthening it? So the quantity I want to study today is how many Neumann eigenvalues do not exceed a given Dirichlet eigenvalue. So there's going to be two pieces of notation throughout the talk that I'm going to ask everybody to make sure you know. And here's the first one. So this nk of omega is notation I'm going to use throughout the talk. And it's always going to mean the number of Neumann eigenvalues that are less than or equal to the kth Dirichlet eigenvalue. So nk omega is that. And so what we just proved, or quote unquote proved, is that nk of omega is always at least k, right? So that's an easy thing to prove using the min-max theorem. And so the new question I want to ask that's more specific is, what is the relationship between the index k, the domain omega, and nk of omega? Okay, so like I said, make sure you know this notation. So are there any questions about the notation or anything before I move on? Okay. So I want to give a quick history of this quantity. There's a family of quantities, and there have been a lot of people who have studied these quantities over the years. Usually they state it as just direct inequalities between eigenvalues. They usually don't use this notation in k of omega. But there are a lot of results that I'm going to state in terms of this quantity. So the first one that I'm aware of is due to Polya. So Polya showed in 1952 that in two dimensions, in one of omega is at least two. So in other words, what he showed is that the second Neumann eigenvalue is always less than the first Dirichlet eigenvalue. And for those of you who are experts in the field, you might immediately assume, isn't this obvious if we combine Faber-Cron with Sego-Weinberger, right? So Faber-Cron says that balls minimize the first Dirichlet eigenvalue, and Sego-Weinberger says that balls maximize the second Neumann. And so if you concatenate these along with knowledge of the eigenvalues of balls, you get this inequality. But Sego-Weinberger came after Polya's proof. So Polya has kind of a from scratch proof that does use favor-Cron, but he has to do a little bit more work. So the next result I want to point out is due to Payne, and so he was able to upgrade this result for convex domains in particular, still working in 2 dimensions, but he got a result that holds for all k simultaneously. So he showed that in k of omega is always at least k plus 2. And so if you rephrase this in terms of eigenvalue inequalities, what he's saying is that the k plus second Neumann eigenvalue is always at most equal to the kth Dirichlet eigenvalue. Um, so this is still pretty restrictive because it's only in 2 dimensions, and it took about 30 years for this to be upgraded to higher dimensions. And the kind of natural analog in higher dimensions is you replace the 2 with the dimension. So what Levine and Weinberger showed in the 80s is that as long as you're still working on convex domains, then n k of omega is at least k plus n. And I should point out that they have other results in the paper. It's not just for convex domains. They have some kind of a more general theorem based on the principal curvatures of the boundary. But I don't want to get into the technicalities of that. But to me, the key takeaway is the result for convex domains. So then in 1991, Friedlander managed to show that he managed to upgrade Polya's result to higher eigenvalues and higher dimensions. So there's no convexity assumption here. There's some technical smoothness assumption on the boundary that was later relaxed by other authors. So I didn't state them here, but basically what he showed was that in dimensions at least 2, nk of omega is at least k plus 1. Right, and so this actual inequality is a little weaker than Levine and Weinberger, but we took away the convexity assumption. So it's kind of assumed that k plus 2 should at least be true in higher dimensions. But to my knowledge, that's still not been done. But earlier so the preprint that I'm about to talk about appeared a couple years ago, but it was finalized and published this year by Jonathan Rohleder that in 2 dimensions, as long as you're working on a simply connected planar domain, nk of omega is at least k plus 2. So this is an upgrade of Friedlander's theorem as long as you're working on simply connected domains. Okay, so those are the 5 results I wanted to point out, but I should mention there are like a ton of papers out there talking about similar things. So this is by no means an exhaustive list. It's just the list of things that have mostly been on my mind as I was doing this work. Right, so I want to give a quick proof of Friedlander's result just to show, I mean, I mostly want to show it just because it's a very quick and easy proof that was found by Filanov a few years after Friedlander's article. And this just kind of gives you a flavor of how do we prove things like this. So it's basically every proof today comes from min-max theory. So I'll just remind everyone in case you don't know that the kth Neumann eigenvalue, and there's something similar for Dirichlet eigenvalues, is given by this, there's a variational characterization of these eigenvalues where you minimize over the set of all k-dimensional subspaces, and within the fixed k-dimensional subspace, you find the maximum of this Rayleigh quotient. So it's the norm squared of the gradient over the norm L2 norm squared of the function. And that gives you the eigenvalues exactly. And there's also uniqueness statement here, right? So as long as if this is actually minimized by some subspace, then that subspace is spanned by actual eigenfunctions. And so what we're going to do is we're going to build some test functions for the k plus, I probably should have written the min-max theorem for the k plus first Neumann eigenvalue, because what we're trying to prove, if you recall from the last slide, is that the k plus first Neumann eigenvalue is at most equal to the kth Dirichlet. So I'm going to construct a vector space of k plus 1 test functions and show that we get the inequality that we want using that. So we're going to use the first k Dirichlet eigenfunctions as test functions, and then we're going to construct one more test function to throw into the list. And to do that, we're going to choose just a unit vector, or not a unit vector, a vector in Rn of length square root of the kth Dirichlet eigenvalue. And the new test function we're going to look at is this e to the I omega dot producted with x. So there's a function that maps x to this exponentiated dot product. And this function is very nice for 2 reasons. So it satisfies 2 different PDEs basically that are very nice. So first of all, it's an eigenfunction with eigenvalue equal to lambda k, which is very helpful. And the other very helpful thing is that the norm of the gradient squared pointwise equals the eigenvalue times the norm of the modulus of the function squared. So basically the second thing, it looks a bit random at first, but what it allows us to do is where when you're doing these like test function type of arguments, when you usually integrate by parts, this allows us to basically just like do like a fake integration by parts kind of because we have this pointwise equality. Um, so like I said, we're going to build a space of test functions to just be the span of all of these functions put together. So the first K Dirichlet's plus this like thing that is often called a plane wave. And it's not too hard to check that the dimension of this space is K plus 1 using the Dirichlet boundary condition, right? So the first K things vanish on the boundary. This e to the I omega x has modulus 1 everywhere. So they're linearly independent. And so the dimension has to be K plus 1. And then from there, all you do is integrate by parts. So what the min-max theorem tells us is that since we have this K plus 1 dimensional vector space of test functions, um, then the K plus first Neumann eigenvalue is at most the maximum of this Rayleigh quotient over this test space. And then when you just do the integration by parts and use these tricks about the e to the I omega x, what you get is that this is at most equal to lambda k. And so what we get when you put all that together is that n k of omega is at least k plus 1. And that's Friedlander's theorem. Okay, so are there any questions about the proof of this or anything before I move on? Okay. So right from here, I want to give a little application of these sorts of results just to give a flavor of like why I got interested in this sort of research in the first place. Um, and I'm going to focus in particular on N1 of omega. So this is the number of Neumann eigenvalues that don't exceed the first Dirichlet. And so there's this proposition that I really like that's very useful in studying nodal sets of eigenfunctions. Um, that was very useful for results related to the hotspots conjecture, but I'm not going to get too much into the details here. But I just want to give a fun proposition that I happen to enjoy, which is that if you have a Neumann eigenfunction whose eigenvalue doesn't exceed the first Dirichlet, then if you look at the nodal domains of this function, which are the connected components that you get when you delete the zero level set, then this eigenfunction has no compactly contained nodal domains. So what I mean by that is that if you have a nodal domain, its boundary has to intersect the boundary of the larger domain in a set of positive measure, using the correct measure. Um, and there's a very quick and cute proof of this, which is just it's supposed by contradiction that there is such a nodal domain. And you just take the eigenfunction restricted to that nodal domain, and on the boundary of that nodal domain, the function equals 0 by definition. And then so you just extend this by 0 to the entire domain. And so you get an h1 function that vanishes on the boundary. And so you get an appropriate test function for the first Dirichlet eigenvalue using this min-max theorem that I talked about in the last slide. And so in particular, what you get is that the first Dirichlet eigenvalue is at most the Rayleigh quotient of this function. But if you integrate by parts, you see that this Rayleigh quotient gives you exactly the Neumann eigenvalue that you started with, which we supposed was less than or equal to the first Dirichlet. And so when you put all this together, you get these inequalities turn into equalities. And using the uniqueness part of the min-max theorem, you see that this phi actually has to be a first Dirichlet eigenfunction, which doesn't make sense because it vanishes on an open set, right? And that's never allowed for Dirichlet eigenfunctions on planar domains. So that contradicts unique continuation, and that's the proof. So, right, and I want to just advertise that this was a key result used in Chris Judge and Sagata Mondal's proof of the hotspots conjecture for Euclidean triangles. So I'm just kind of stating that for people in the room who happen to know about the hotspots conjecture, that's not really what the topic of the talk is. But this application of it is kind of why I got involved in this line of questioning to begin with. So I thought I'd share that. Okay, so far everything we've talked about have been kind of universal inequalities that hold for all of some family of domains simultaneously without much respect to the geometry of the domain. So the only sort of hypotheses in the last theorems were just is it convex or not? Is it simply connected or not? But nothing about the actual like intrinsic geometry of the shape beyond those basic or like kind of like coarse geometric quantities. So I want to start thinking a little bit about how does the geometry actually affect these quantities. And I'm going to focus for most of the talk today, but just because most of my results are about N1 of omega, that's mostly what I'm going to talk about. It's harder to say things for like this for higher Ks, but I'll maybe discuss that a little bit later. Um, so I want to just look at the example of rectangles just to build some intuition. So let's look at the family of rectangles that are just the interval 0 to L cross 0 to 1 with L at least 1. So that I guess I should have pointed out earlier that these nk of omegas are all scaling invariant. right? Because when you rescale a domain, it rescales the Neumann and the Dirichlet spectra by the same constant simultaneously. So the nk omegas stay unchanged when you rescale the domain. So this is kind of a one parameter family of rectangles that up to scaling covers every possible rectangle, right? Um, and this is a basic exercise everybody does when they start learning this subject, is how to compute the eigenvalues of these things. So you just use separation of variables. And what you see is that the first Dirichlet eigenvalue is pi over L squared plus pi squared, and the Neumann eigenvalues are given by expressions of this form, I pi over L squared plus j pi squared, where I and j are now at least zero, or they're integers that are at least zero. Whereas for the Dirichlet spectrum, you have to start at 1. And so this is another reason why you should expect Neumann eigenvalues to be less than Dirichlet. And if you just run the computation, you see that in one of this RL, you just put these inequalities or these equalities into the inequality you want to solve. So and I canceled the pi's here in the computation. So you want to know how many non-negative integer pairs are there, ij, such that I over L squared plus j squared is less than or equal to 1 over L squared plus 1. And if you just do the easy thing and assume that j equals 0 and you're looking for the I such that I over L squared is less than or equal to 1, you can see that the size of this set is is at least equal to L. Um, and since I've done this weird scaling thing, it might not be extremely clear to you at first, like what this L is representing geometrically, because I mean, L is the area of the thing. It's also like kind of related to the perimeter. But what I claim is that what this L is actually representing is this isoperimetric ratio of the domains. And so that's kind of the intuitive picture that comes from rectangles. So this was actually put into a conjecture of Freitas and Gamma earlier this year. Um, so here's the second piece of notation I want everybody to make sure you're aware of before I move on with the talk, and this is the isoperimetric ratio. So anytime I write I of something, capital I of something, it's going to be the scale invariant isoperimetric ratio. So it's the size of the boundary to the n over the size of the domain to the n minus 1. Um, and you can check that this is scaling invariant, which is good because we're wanting to compare another scaling invariant in a quantity to this one. So make sure you know what that is, and then should be good for the rest of the talk. And so what the conjecture is that came out earlier this year is that there exists some constant in 2 dimensions such that for any convex domain, n k of omega is at least k plus this floor function, but the floor is just to give us a little wiggle room. The point is basically that it's k plus something times the square root of the isoperimetric ratio times k. So it's k plus square root of k with some constant, and the claim is that this constant depends on the isoperimetric ratio. And the reason that this is kind of natural, so the fact that there's a k here is kind of obvious from the earlier slides, right? We already showed that in k of omega is at least k. So the question is, how much does it exceed k by? And if you look at domains that have two-term Weil's laws, then you can kind of come up with an asymptotic value of this for large k as k goes to infinity. And it's not too hard to show. You can see it in the preprint of Freitas and Gamma that the growth rate is like k plus square root of k, but there's some constant on the square root of k. And what they're conjecturing is that this constant for convex domains in particular is determined by the isoperimetric ratio in this way. And they managed to prove this conjecture for rectangles. So that's and this is still a wide open conjecture that I would very much like to solve, but I have not done so yet. Right, so that brings me to the first main theorem I want to talk about today, and this is kind of like the biggest result in the preprint that I want to talk about. So around April of this year, I put out a preprint that has three main theorems about this quantity in 1 of omega with respect to isoperimetric ratios, and this is the first of the three. So what it states is that for convex domains, there exist these universal constants such that n1 of omega is bounded above and below by the isoperimetric ratio. So I want to emphasize that this N1, or that the theorem is just for N1. It's not for NK. And also for the particular case, the K equals 1, this is also a bit stronger than the Freitas-Gamma conjecture, right? Because there's no square root in this. It's just the isoperimetric ratio. But it's different because it's not stated for all K. It's stated just for K equals 1. And then the second statement of the theorem is that this same statement is strictly false for non-convex domains. And I'm going to talk a little bit about the counterexamples in the next slide. So that's the theorem, and 2 remarks are in order about the theorem before I move on. So first of all, me proving this theorem was motivated primarily by a preprint of Cox-MacLachlan-Steeves, who conjectured that the first statement should be true for all Lipschitz domains. And they managed to prove the result for rectangular prisms. And so their proof for rectangular prisms is kind of a key point of my proof of this theorem. And reading their preprint is what motivated me to think about this in the first place, or about this particular set of inequalities. And I should also point out that beyond their result for rectangular prisms, this is the first result that I know of that gives an upper bound on n1 of omega. So not just a lower bound, but an upper bound as well. Right, so that's the theorem. And so now before I will talk a bit about the proof, but I want to talk about the non-convex counterexamples first. So why is this false for non-convex things? So there's two different inequalities. So there's two different families of counterexamples I want to talk about. So the first is a counterexample to the lower bound. So a counterexample to showing that the n1 of omega is bounded below by the isoperimetric ratio. So the basic idea here is that you're going to take a sequence of domains whose isoperimetric ratio is going to infinity while the domain itself is kind of converging to a somewhat nice domain. So the actual particulars aren't so important, but the example that I wrote up the details for in the preprint are examples of the form in the figure here, which is just a disk with spikes attached to it. So there's roughly k² spikes with height 1 over k. So the astute observer will notice that this gives me a perimeter of roughly size k. So as k goes to infinity, the isoperimetric ratio is going to go to infinity. And the area stays bounded, right? Because it's converging to a ball in a certain sense. I guess Hausdorff converging, for example. And then what you can also check is that the eigenvalues of this thing are converging to the Dirichlet and Neumann eigenvalues of the ball, right? So both spectra converge to the unperturbed spectrum. And so in particular, n1 of omega k converges to n1 of the unit ball, which I denote by B. And that happens to equal 3, which is a pretty finite number, whereas the isoperimetric ratio is going off to infinity. Right, so this gives me a counterexample to the lower bound because we have an unbounded family of isoperimetric ratios, but a uniformly bounded set of n1 of omegas. Okay, and then what about the upper bound? So the upper bound's a little bit trickier to actually come up with, but it's basically a rooms and passages sort of domain. So these sorts of domains were originally found as, or to my knowledge at least of the literature, these were originally constructed to give counterexamples to having a discrete Neumann spectrum. So if you take like the limit of the domains that I've drawn here, so you have like infinitely many T-shaped domains that are shrinking to a point kind of, then that domain will have a central Neumann spectrum. And so what we're doing is we're taking a sequence of domains that limits to that one. So for each k, omega k is the union of like k T-shaped domains that are each shrinking exponentially, and while also the ratio of the width of the arms are also shrinking exponentially with respect to the size of the kind of blob in the middle. And so if you do this in the right way, you can do it such that the isoperimetric ratio stays uniformly bounded because the perimeter and the area both stay uniformly bounded. But using a test function argument where you basically construct test functions whose L2 mass is mostly supported in each blob, you come up with k test functions, each of which has its mass supported mostly in like the thick part of the T, and it decays to 0 in the thin part of the T. This gives you a nice test space of functions that shows you that all the Neumann eigenvalues are very small compared to the first Dirichlet, and so you get the n1 of omega k is at least k. So we get a conjecture or counterexample to the opposite inequality. So those are the two counterexamples. So I'll maybe pause for questions there in case there are any about the counterexamples.
Yeah. Actually, I would have a question if that's all right. So it's clear that the first counterexample you can you can make it for a star convex domain by putting the spikes more like around the disk rather than
Right.
whereas the one on the right is in a way very non-convex. I mean, it's clearly not star convex either. Do
Right.
you think that for star convex domain you would at least have one side of the inequality?
Huh. That is a very good question that I have not thought about before. My instinct tells me that you can't come up with star convex counterexamples in this case because, um, well, actually, maybe not. Well, the only way I know to come up with counterexamples is to have sort of rooms and passages, like, right? Because if you want very small Neumann eigenvalues, you want to have a highly disconnected domain, and I guess star-shaped things aren't super disconnected, if that makes sense. But I don't know.
Mm.
I have no idea. That's a very good question.
Yeah, okay. I mean, I'll mull on it, but thanks.
Yeah, okay. Yeah, thanks for the question. That's a very interesting question. So I want to talk next about some of the proof ingredients for the theorem because it's actually quite simple to prove if you're not super interested in keeping track of the constants. So the first key ingredient in the proof is the John ellipsoid theorem. So this is a theorem that I think everyone in spectral geometry should know, that I did not know before I started working on this project. So I think this is a good chance to advertise it and make sure more people learn about it. So what this says is that for any convex domain, there's a unique largest ellipsoid by volume that's contained in the domain. And the cool thing about this is that when you translate the ellipsoid to where it's centered at the origin, and then you dilate it by a factor of the dimension, then it actually contains the domain. So the important point is that there's kind of a universal constant such that there's an ellipsoid inside where if you dilate it by that universal constant, it goes outside the domain. And the basic idea of the proof is I'm going to compare the eigenvalues of a general convex domain to something on the inside and something on the outside. Um, but the annoying thing is that eigenvalues of ellipsoids are a little bit hard to describe, right? So they're like semi-explicit, but not in a super useful way. So instead of using ellipsoids, I turn these into what I call John rectangles, which is not an official definition, but it's just what I happen to call them. So you can take the John ellipsoid and put this kind of distinguished rectangular prism on the inside, and then put one on the outside of the dilated version. And what you can check is that you can do this in such a way that you can dilate the inner rectangle by a factor of the dimension to the 3/2 to get a rectangular prism on the outside. And so this is kind of a version of the John ellipsoid theorem, though I should point out you lose uniqueness and stuff like that, but that's not important for the proof. The important part is that there's this universal constant once again, such that you can dilate your rectangle to get on the outside. So I have a little schematic here on the bottom right of the slide in case you're trying to keep track of the mental image you should have. So the important point of the slide is that there's a rectangle on the inside and one on the outside, such that they differ by a universal constant dilation factor. Um, and then how do we actually compare the eigenvalues and the isoperimetric ratios of these things? So the next lemma is another fact from convex geometry that I think everybody should make sure they know at some point. Is that is basically just that the surface area of a convex body is monotonic with respect to domain inclusion. So if you have one convex domain inside of another, then the perimeter of the smaller thing is smaller than the perimeter of the larger thing. And this is once again, something that strictly falls for non-convex domains. That's not hard to show. And so what you can, and since we have this like universal dilation factor, what this gives us is that the isoperimetric ratio of the rectangular prism is bounded above and below by universal constant multiples of the isoperimetric ratio of our starting domain omega. Okay, and then so that's how you get from the isoperimetric ratio of one to the other. And then you want to ask about what about the eigenvalues, right? So the first ingredient is Dirichlet domain monotonicity. So hopefully everybody in the Zoom knows about this. So all this says is that there's a kind of order reversing inequality between Dirichlet eigenvalues. So if you have a smaller domain, the Dirichlet eigenvalues get larger. And so this allows us to compare the eigenvalues of the omega to the eigenvalues of the bigger and the smaller rectangle. And then there's a new theorem of Funano that I think is very interesting, which basically, there's a very annoying fact in spectral geometry is that domain monotonicity fails for Neumann eigenvalues. So it's just strictly not true. But what Funano managed to show is that as long as you're working with convex domains, then it is true up to a constant multiple. So there's a universal constant in each dimension, such that if you have one convex domain inside of another, then the eigenvalues satisfy the opposite in a opposite bound, right? So once again, smaller domains give you larger eigenvalues up to a constant. And the very cool thing about this to me is that this constant works for every eigenvalue simultaneously. So this isn't just for the second Neumann eigenvalue, it's for all of them together. And so those are basically all the ingredients you need to prove the theorem. So let's just put all those together now. So I'm going to start with my
Yeah,
rectangular.
can I
Oh,
stop you for a second? Do you know in that theorem by Funano if do we have any sort of control on this constant in terms of the dimension? Do you know how
yeah,
it
yeah.
grows or something?
Right. Yes, yeah. So the constant grows like n squared. So he actually, if you look at the way he actually states the theorem, it's that there's a universal constant independent of the dimension, such that this is true with c replaced by c times n squared. Yeah, that's a good
Ah,
question. And
thanks.
that's yeah, and that's actually like the optimal growth because he gives some examples showing that's actually optimal. But the constant itself that goes in front of the dimension, that's still an open problem what the optimal thing is. Um,
Mhm.
yeah. So, right. So let's go to the proof. So we're going to let R be that John rectangle that I talked about. And then if we just put those domain monotonicity theorems together that I mentioned, what this says is that there's some universal constant C that depends only on the dimension, such that in one of my convex domain is bounded below by the number of Neumann eigenvalues of the rectangular prism that don't exceed C times the Dirichlet eigenvalue. So it's almost like saying n1 of omega is greater than or equal to n1 of the rectangle, but there's this constant thrown in. Um, but then beyond that, the eigenvalues of a rectangular prism are very explicit in terms of the edge lengths of the rectangular prism. And so the right-hand side of this is bounded below by you just do some elementary estimates on like counting the number of non-negative integer lattice points in a certain ellipsoid. That's just what the proof turns into if you look at what these eigenvalues actually are. So this isn't the full proof. You have to still do that counting problem, but it's pretty standard the way we estimate this. And it turns out that this quantity is bounded below by the volume of a certain ellipsoid, where if you compute the volume of that ellipsoid, what falls out is exactly the isoperimetric ratio of this rectangular prism times some constant. And what we showed on the last slide is that this isoperimetric ratio is bounded below by a constant multiple of the isoperimetric ratio of our starting domain. And so what I've proved so far is just the lower bound on n1 of omega, but the upper bound is basically the same thing. There's a slight tweak in counting on estimating the number of lattice points in the ellipsoid, but it's also a pretty standard argument, so I'm not going to get into it. Um, but yeah, that's pretty much the proof. Right. So are there any questions about the proof before I move on to other things? Okay, so next I want to talk more about non-convex domains for a moment. So it's still pretty like the non-convex domains that I showed you as counterexamples are pretty pathological domains, right? And if you look back at the preprint that motivated me working on this by Cox-MacLachlan-Steeves, they have some pretty compelling evidence that there is still some sort of relationship for like maybe non-pathological non-convex domains. So what they do to find evidence for their conjecture is they randomly generated polygons and found both of these quantities for the polygons. And so here on the left, you can see a picture of an example of a randomly generated polygon, which is taken from their preprint. And then on the right, there's a plot where they did this for like 11 or 12 different polygons with up to 30 sides. So you end up with polygons that are highly non-convex and with very large isoperimetric ratios. And if you look at the plot, it looks like there's a pretty strong linear relationship between the two quantities, right? So you still so something I expect is that there should be something true, some true relationship between these two quantities for non-convex domains, as long as you don't have as long as you don't allow for like weird pathologies. But it's a very hard question to say how do I rule out pathologies? Like what is a pathology here? So one thing that I managed to do is look just at polygons. So in R2. So what I managed to find is that there exist universal constants once again, such that n1 of omega for an m-gon, so a polygon with at most m edges, n1 of omega is bounded below by a multiple of the square root of the isoperimetric ratio and bounded above once again by the isoperimetric ratio. In both cases, you can see the dependence on the number of edge lengths. So these constants, little c and big C, are actually independent of m. But you can see the M dependence in the actual inequalities. Um, and so that's the result I managed to find. And something you might be wondering about is where is this square root coming from, right? So in my original theorem, there were no square roots. It was just isoperimetric ratios. But it turns out that up to the constant, as long as you're working with at least four sides, this square root is actually necessary. So for three sides, the set of m-gons are all convex, and so the original theorem is stronger. But as soon as you have four or more sides, you actually have to have this square root. Um, and the example is given here by you fix a right isosceles triangle and then you attach a very long and narrow right triangle to it. So this is a foregone. And so this long and narrow triangle has legs of size k and 1 over k. So as k goes to infinity, you can check the isoperimetric ratio goes to infinity. Because the area stays uniformly bounded, but the perimeter goes to infinity. And using some other like domain monotonicity and eigenvalue estimate tricks, you can show that the growth rate of the eigenvalue of n1 of omega k is bounded above by a constant independent of k times the square root of the isoperimetric ratio. So what this shows is that the lower bound is sharp modulo the constant that I've used. Um, Right, and I don't want to talk about why this inequality is true because it's a bit technical, but I want to give you just a little bit of a reason why this is kind of like the shape that makes sense to be um, the sharpness example. So basically, when you prove the last theorem, so I did these tricks with the rectangles and stuff, but if you really look at it, what you'll see is that what I'm doing is I'm bounding the first Dirichlet eigenvalue from below by something related to the isoperimetric ratio, and I'm estimating Neumann eigenvalues from above by something related to the isoperimetric ratio. So like in both cases, it's by something with like slightly different exponents that like when you put them together, the actual isoperimetric ratio falls out. But in this case, for non-convex domains, you can imagine having like most of your mass in some blob and like a very thin tail, like you have in this example. What happens when the tail is long and thin enough is that the Dirichlet eigenvalue doesn't really care about the tail so much as long as the area of the tail is negligible compared to the area of the blob. Right. So instead of estimating the first Dirichlet from below by the isoperimetric ratio, the best thing you can do now is favor cron, is compare it, is use an area-based comparison to the eigenvalue. And so that's basically why we have to pick up the square root in this case. So that's the best possible thing for m-gons. But I should also mention, I don't know that this dependence on m being m squared is optimal, and I don't know anything about optimal constants or anything, but I know about the growth rate with respect to the isoperimetric ratio. Okay, so I think that is all I wanted to say about planar domains before I move on to manifolds. So, right, so all of the results I've stated so far have all been completely Euclidean, but over the years there have been a number of generalizations of these things to non-Euclidean spaces. So I'm going to give you four examples of these, but once again, this is a very non-exhaustive list. There's a lot of results out there about similar things. But these are just ones that kind of stood out to me. So the first three of these four that I'm going to state are basically just generalizations of Friedlander's theorem. So remember, Friedlander's theorem said that in Rn, as long as you have a nicely bounded domain, then nk of omega is at least k plus 1. And that's going to be the upshot of all three of the first three of these theorems. So the first is due to Mazzeo, who took it was basically looking at Friedlander's proof, and his paper is about like where can you generalize Friedlander's proof. And so one example of what he finds is that as long as your domain is contained in a symmetric space of non-compact type, for example, hyperbolic planar domains, then Friedlander's theorem holds. So nk of omega is at least k plus 1. Um, and something else he shows is that, so if you recall back to the slide a long time ago about how to prove Friedlander's theorem, what you did was you came up with this test function that was like a plane wave, right? So it was an eigenfunction of the Laplacian that happened to also have the property that the norm of the gradient squared pointwise equals the norm of the function squared times the eigenvalue. And what Mazzeo shows is that such a function can't even exist locally on certain positively curved spaces. So he's basically testing the limits of Friedlander's argument. Um, and in general, you shouldn't expect Friedlander's theorem to hold in spaces of positive curvature, because something you can imagine is if you just take like the round two sphere and delete a very small puncture from it, or delete a very small disk from it, then the Neumann and the Dirichlet spectra are both converging to the spectra of the whole sphere as the size of that disk shrinks to nothing. And if you just look at what happens to the eigenvalues, what happens in the limit is that eventually the second Neumann eigenvalue is greater than the first Dirichlet, just because you're converging, both spectra are converging to the spectrum of the sphere. So for positively curved things, you shouldn't expect this to hold, but Ashbaugh and Levine managed to actually show a positively curved example of spaces where this holds. So what they showed is that if you're looking at a domain contained in the sphere that has whose boundary has non-negative mean curvature, so this is a condition that kind of forces your domains to not be too large in a sense. So for example, convex subdomains that aren't the entire sphere have this property. Then once again, Friedlander's inequality holds. And then more recent, and I want to, the last two results I want to give are basically, I'm mostly giving them because they're very recent results. So very recently, Frank, Helfer, and Laptev showed Friedlander's inequality for acting on subdomains of of certain Carnot groups with the sub-Laplacian. So something that I'm not going to, this is like the only place in the whole talk that I'm going to mention this, is that there are also generalizations of these sorts of theorems to other elliptic operators. So it's not always just for the Laplacian. And here's one example is working with the sub-Laplacian. So for those who don't know about Carnot groups, these are Lie groups whose corresponding Lie algebra has kind of a distinguished set of generating subspace that generates it in a particularly nice way. And it's a strict subspace. So basically there's and by translating the Lie algebra around the Lie group, this basically gives us a, a smaller dimensional space of every tangent space that the Laplacian acts on. So this particular sub-Laplacian is acting in the directions of this generating subspace of the Lie algebra. And they managed to show Friedlander's theorem for these sub-Laplacians acting on these Lie groups. Okay, and then finally, a generalization of Rohleder's theorem. So remember I said on my last history slide that what Rohleder showed earlier this year / 2 years ago, depending on if you want to go by the preprint or the publication, is that for simply connected domains, in K of omega is at least K plus 2 in 2 dimensions. And so what Hua, Munk, and Zhang showed this year is that if you have a subdomain of a Riemannian surface, that is simply connected and such that the Riemannian surface satisfies a certain technical curvature condition, which roughly speaking, you should think about as just being like a kind of negative curvature condition, then N1 of omega is at least 3. So those are the results I wanted to go through. I am not an expert on these results, but I do want to give one theorem about Riemannian manifolds. So, and this kind of also came out of me being unsatisfied with the non-convex domains thing, like the fact that my inequality didn't hold for non-convex domains was annoying to me. So something I thought of that or a nice class of non-convex domains where the inequalities do hold is tubular neighborhoods of submanifolds. And it turns out that this generalizes well to submanifolds of any Riemannian manifold. It didn't actually have to be Euclidean. So what the theorem says is that if you have a closed submanifold of some ambient Riemannian manifold, so M is compact in particular, X is not necessarily, it might be, that would be fine if it were. And then we're going to look at the epsilon tubular neighborhood of M. So this is the set of all points in X that are within epsilon geodesic distance to M. And what the theorem says is that as epsilon goes to 0, I have an exact asymptotic on N1 of omega epsilon. And this exact asymptotic is that there's a universal constant that just depends on the dimensions times the isoperimetric ratio. So I guess something that I should point out is that as epsilon goes to 0, the isoperimetric ratio of this thing goes to infinity. That's a simple exercise in Riemannian geometry. And so N1 of omega epsilon is going to infinity, and the exact rate that it's going to infinity is this constant times the isoperimetric ratio with a little o term. And I also, just as a warning, I'm about to show you a very nasty formula for the constant here. So the constant, I mean, it doesn't matter so much what it is, but I basically just wanted to show you that it's explicit. Like I know what it is. So these little omegas are the volumes of Euclidean unit balls, and capital B, wherever there's a capital B, that's also a Euclidean unit ball. So it's something that's kind of interesting is that as epsilon goes to 0, the epsilon tubular neighborhood of M starts to kind of look like like a Euclidean epsilon tubular neighborhood of M. And so it turns out that that's why we kind of don't have any sort of dependence on the ambient manifold X. All that matters is epsilon and the dimensions that we're working in. So that's the theorem. And this is the only place that I know of where you have a family of any sort of geometries where you have an exact asymptotic on this quantity N1. So I'm going to end by giving a very sketch or a sketch of a very easy case of the theorem. So in general, this epsilon tubular neighborhood is like a fiber bundle over M, right? Which is kind of a complicated and annoying thing to work with. But the way the proof works is you start by proving the trivial case and kind of build your way up from there. So I'm just going to talk about the trivial case. I'm not going to talk about how to get to the whole theorem from there. So in the trivial case, omega epsilon is just the Cartesian product of M with a Euclidean ball, an epsilon Euclidean ball. Um, and in this case, you can do separation of variables, right? So you can say that the Neumann eigenvalues of this omega epsilon are exactly sums of eigenvalues of M with 1 over epsilon squared times eigenvalues of a unit Euclidean ball. And lambda 1, since M is a closed manifold, lambda 1 of omega epsilon is just 1 over epsilon squared times lambda 1 of a unit ball. And then we're just going to compute things. We're just going to put these together and count what we can count. So first of all, when epsilon is sufficiently small, if mu k of the ball is larger than lambda 1 of the ball, then we don't get the inequality we want. We don't get mu j less than lambda 1. And so if we're counting this or so we can count this term by term with respect to this parameter k. And the terms with k larger than in one of the Euclidean unit ball are going to give us 0. So this book turns into a nice finite sum. And then in the next line, I basically just rearrange this inequality to get the Neumann counting function for the manifold M, right? So this math cal n is the eigenvalue counting function for M, and it's pretty easy to go from the first line to the second, right? So I've just subtracted a term to the other side. And the nice thing now is that as epsilon goes to 0, this quantity inside of the counting function is going to infinity. And so the words that you should be screaming in your head now are Weil's law, right? So Weil's law tells us exactly, or an exact asymptotic on this counting function. And so you just apply it term by term. And this is a finite sum, so I can take the little O term out of the whole sum. And then I can factor all the constants out of the sum that don't depend on k. And so what I get on the left-hand side is almost that constant I showed you on the last slide. And then, but the important part is that there's this nasty constant times the volume of M over epsilon to the M. And then it's once again another exercise in Riemannian geometry to turn this volume of M over epsilon to the M into the isoperimetric ratio of the whole thing. So these are related, or these quantities are related to each other by a constant factor that just depends on the dimensions. And so that pretty much gives you the proof of the easy case. And then to upgrade this to different manifolds and to the case where omega epsilon is a fiber bundle, it takes some extra tricks and some perturbation theory, but nothing too hard. This is kind of the heart of the argument that gets us to the actual asymptotic. Okay, so that's all the proofs I wanted to talk about today. So are there any questions about the proof of this before I get to my last thing? Okay, so yeah, I mean, this is kind of a nasty computation, but it's actually like pretty straightforward if you just look at it. Okay, so I want to just end by pointing out that I've answered some questions about these quantities, but there are a lot of questions left to be answered that I'm very interested in tackling. So first of all, something I didn't talk much about are the actual constants in the theorems. And several spectral geometers I've talked to have been like, what are the best possible constants? And I think that's a very interesting question, especially in the first theorem about convex domains. This is something I'm interested in tackling. And a corresponding question that comes out of this is, are there extremal domains for these things? And if so, what are they? So in other words, are there extremizers of n1 omega divided by the isoperimetric ratio? So are there maxima and minima? Because for convex domains, these are bounded above and below by some universal constants. Right. Next goal is I would really like to prove the Freitas-Gamma conjecture because it feels almost like the proof I gave for N1 should work for that conjecture, but it actually doesn't. And basically, this is because if you look back at what their conjecture was, it was that Nk of omega is at least k plus something times k to the n minus 1 over n. And the annoying or the part of my proof that doesn't work here is that what they want to prove has like kind of an exact k in it. There's no k times a constant. It's just exactly k. And so that kind of breaks the proof. So it doesn't quite work here. Okay, and then moving on, I would like to generalize these theorems to manifolds with boundary. So I gave you one theorem about manifolds with boundary. but these are very particular families of such manifolds. So I would like to say things, for example, about hyperbolic surfaces with geodesic boundary or other such things. And then finally, I think another interesting line of questions could come from thinking about Robin boundary conditions. So that's usually the next step in spectral geometry after you prove a theorem is, can I prove a Robin version of it? And it's easy to make I guess it's hard to make conjectures about the Robin thing because you also want to conjecture like what is the role of the Robin parameter now. So there's a whole new parameter to talk about when you're asking such a question. And I don't really even have any concrete conjectures to state about this, but I think it would be very interesting to know what happens when you change the boundary conditions like this. So maybe you're comparing two Robin spectra or Robin to Dirichlet or Robin to Neumann. So that this basically just gives us a whole new dimension to ask questions in. So those are some of the areas of future work. And I think I'm going to stop there. Thank you very much for listening.
Thanks a lot, Lawford, for this very good talk. And we have some time for questions now. So if you have some, don't hesitate to unmute yourself or
Ask a
put them in the
question,
chat.
please.
Yes, of course.
Hello. Can I ask a question?
Yes, of course.
I just wonder, you did not mention the trace formulae, which are of course not as sharply defined, but Weil formula, for example, for the leading term, the smooth term, is known to fourth order in the approximation. And especially if there is a very good expression for the dependence on the Robin parameter by a work by Martin Sieber. So I wonder why didn't you, or I should say, ask a different way. Suppose that you take the trace formula and the first, the smooth part of it, as much as is known, and just compare the number counting function which you get from whatever you need, the Dirichlet and Neumann, and does it give you any information?
For I'm sorry, for which sort of theorem?
The trace formulae usually have one term, or it's called the Weil term, which is the smooth part of the number function, and then there are the corrections which are due to periodic orbits. Now, suppose that you take the smooth part and you compare them, and you can compare them order by order according to their magnitude. And then I remember that there is a difference between Dirichlet and Neumann. Usually it is a difference between in signs.
Right,
Terms.
yeah. So
The question is whether you can get some information about it, and in particular, because the trace formula are known for continuous variation of the Robin parameter, then you can see how the Robin parameter
right.
tendons
That would
look like. And of course, it is assuming that the surfaces are, and it is known for two-dimensional systems, not for more, and it is known for sufficiently smooth boundary plus corners. You can also add the corners corrections. So my question is, what do you learn from there?
Right. That's a very good question. So I've never considered this actually. And what I would guess is that the sort of theorems you would get out of this would be something like the Freitas gamma theorems that I didn't write their theorem, so that I wrote their conjecture. But they have some theorems in their preprint about this nk of omega as k goes to infinity. So since these heat trace formulas kind of use all of the eigenvalues simultaneously, my guess would be that this would at best give you things about the nk of omegas as k goes to infinity. But for like n1 of omega or for some particular set of k's, it's not clear to me that that would give you much. But I do think that would be interesting to look at because
There is a
use
very good paper which is written by Martin Sieber and some other people back in the where is it 90 or some of the last century or 2000 and something, just before you were born. But it is it has a complete description of the trace formulae for billiards up to high orders. And then you
right.
can, and it is proved over there using the Green's function, etc. So you can have a look at it.
Yeah, that would be interesting to look at. Yeah, thank you for
Okay.
this.
Thank you very much.
May I reply a little bit to Uzi's question? Uzi, say if you want to use trace formulas to get from trace formulas to actual inequality, you need some kind of Tauberian theorems. And Tauberian theorems, they work well for kind of growing function, like the counting function, like that. But when you compare, you take the difference. And the difference behaves rather widely. It's not, there is no monotonicity, and Tauberian theorems usually are not well suited for dealing with this one. This is, as far as I can see, it's a big problem. How to, if you want to translate trace formulas to actual estimates for these functions.
Well, you know, in physics, we believe in trace formulae.
Oh, yeah, I know.
Thank you very much, Uzi and Linnea. Do we have other questions? I see a raised hand from Marcello.
Oh, hi. Thank you so much. And thank you so much for your nice talk, Lawford.
Thank you.
And then I have just a curiosity, I mean, because you told the story for, let's say, the low energy, let's say, part really of this narrative, so in particular for N1. So I was wondering, what happens when instead you consider NK and for bigger K, let's say? In particular, I was looking at your geometric inequalities. So do we know if something like that work? Well, something like that works also for NK or K big.
Right, yeah. So for higher K, it's exactly this Freitas-Gamma conjecture that we're expecting. But the proof of the theorem just does not work in that situation. But yeah, so what I expect is this. So instead of nk of omega being bounded below by just the isoperimetric ratio, what you expect is that it's bounded below by k plus square root of the isoperimetric ratio times k. And the square root's basically coming out of like taking very large k. And something that I have a very vague idea about that I don't know how to actually explicitly state it is that as k goes from 1 to being large, there's going to be some interpolation between going from the actual isoperimetric ratio to going to the square root. But yeah, so this is the conjecture, and this is kind of like the shape of this conjecture is basically as good as it can get. If you take k to infinity, you can, using two-term Weil's laws, you can get that. So this is the best I would expect to actually be able to prove for all k.
I see. Thank you so much. Yeah, I was wondering if there was some, I don't know, weaker result known. Or...
Right. Yeah. To my knowledge, I don't know of any results that hold for all k's that aren't stated on rectangles. So there are things on rectangles, but that's pretty much it.
Thank you so much indeed again.
Thank you, Marcello, for the question. We have another one from Michel Karpukin.
Hi. So I agree that N1 and K in general seems like a nice, interesting quantities. I wonder, can you repeat the motivation for why we're comparing it with the parametric ratio necessarily? Why don't we look at some other scale invariant things?
Right. I mean, the answer I want to say is just because it turned out to be what was correct. But yeah, so I mean, I kind of landed on this because it was conjectured by the Cox-MacLachlan-Steeves paper. But I think the conjecture probably comes out of looking at rectangular prisms. So I had this example computation for rectangle. This is just a two-dimensional rectangle. And so what I got was basically the N1 of RL looked like L, which is not super enlightening because, like you said, this could represent some other geometric thing. But if you look at higher dimensional rectangular prisms, then it becomes a little more apparent. Like, so you can run basically the same computation on the rectangles and see that what falls out is actually the isoperimetric ratio.
Okay, are you saying this is in which paper?
It's Cox-MacLachlan-Steeves. It's called like isoperimetric relations between Dirichlet and Neumann eigenvalues.
Okay, it basically makes it clear that there's no other reasonable quantity you can write.
Right. So I will say something that I thought about for quite a while was could you replace isoperimetric diametric, right? Because like for non-convex domains, you could talk about like the intrinsic diameter with respect to the path distance. And the counterexamples I showed here don't have very large isodiametric ratios, so maybe these are good. Maybe that would be a good contender. But it turns out that you can actually come up with a counterexample to the lower bound for that thing too. So if you take the exam, I have this in the preprint. It's a domain bounded by basically the graph of a Gaussian. Chop it off and then take where you cut it off to infinity. It turns out that what you're converging to is something with discrete spectrum, but with infinite isoperimetric ratio. And so you can't replace it with diameter, but I guess that doesn't rule out why you can't do anything else. But yeah, that's one other contender you could have thought of.
Okay, just to summarize, so there are basically two, counting yours, 3 papers which consider those inequalities, right? And
yes,
and
yeah,
no one else considered any other inequalities for NK?
not to my knowledge, no.
I think we all agree that Petrov type P is necessary.
Thank you, Misha, for the questions. Do we have any other questions for Lawford?
Maybe I'd like to ask one question. Thanks for the awesome talk, by the way. This
Yes,
tube
go on.
formula is fascinating that you get the last thing that you talked about. And I was wondering, did you think about the next terms? I suppose you could compute them and they're probably gonna be similarly beautiful.
As in the next term in the expansion or
In the
the
little old one, yeah.
Oh, right. Yeah, so I thought about this briefly. I haven't thought about this since I wrote the paper, but I think I convinced myself you can't get another term without
Oh,
yeah, because well, there's a very general issue, which is that you're working in a general ambient manifold. And so this little O term can like also contains error terms on like the estimate of the isoperimetric ratio, for example.
yeah,
Uh,
but there's Weier's tube formula, which tells you that the next terms in the volume, for example, are some characteristic classes and so on. And
and I would need to
it
look
would
at
be
it.
really funny to see this
I
married
believe,
with Weier's law
yeah,
for eigenvalues.
right. I don't recall. I think maybe you needed 2 terms in the Weil's law if you wanted another term as well. Like there are multiple
Mm-hmm.
bad things that go into this little O term. So that would be very interesting to look at, but I have no idea what that would end up giving you if it could give you anything.
I mean, the leading
That's
constant
a
is
really
already
good
super complicated. I mean,
right.
congrats for getting this. It looks super cool.
Thank you for the question. Do we have any other questions for today? Well, I mean, definitely looks like your results were appreciated and that the audience found it engaging. Thank you a lot again, Lawford, for this very nice talks. We'll reconvene next week. We will send you as usual in the middle of the week the information for next week's talks.